G'day and welcome back to RC Model Reviews. Today I'm talking about ducts, propeller ducts. I received these a little while ago, did a video on them, came from Australia, 3D printed propeller ducts for mini quads, or anything really. And a lot of people ask, well, how do these work? How are you going to increase performance of a propeller by putting it in a duct? And it's a very good question. And it brings quite a number of elements of physics and aerodynamics into play to understand how these ducts can actually improve the performance of a propeller and a motor combination. And they'll improve it in theory by giving you more thrust for the same amount of power, or requiring less power to achieve the same amount of thrust. The bottom line is your battery should last longer and you should get longer flight times out of your flying machine, whatever it may be. So what I'm going to do now is just look at some of the principles, the basic principles, and we'll look at how they apply to these ducts. Now, the first of these theories we need to look at is one proposed by Mr. Bernoulli. It's his theorem, and it's all to do with air pressure. And let's assume we've got a flat sheet of anything here, a flat plate. I've drawn this line. It's a very accurate representation down to the finest detail of a flat plate. And in a normal situation, if this flat plate had no weight, for example, it would just sit there in mid-air, right? It wouldn't go up or down, it would just sit there, assuming the air was completely calm, because the forces pushing on the bottom of this plate would be equal to the forces pushing on the top with air pressure. The air pressure is balanced all around. And so, hey, that's fairly straightforward. But now what happens? What would happen if we actually directed a flow of air across the top of this plate like this? Anybody got any ideas? I know lots of people do. Lots of people already know this stuff. For the benefit of those who don't, I can tell you the plate would rise up. And it would rise up because Bernoulli's theorem says that where air or a fluid is moving, the pressure is lower. The pressure is lower where the fluid is moving. So because we've got air moving across this way, the pressure being exerted outwards is lower. And that means the pressure underneath, the normal air pressure, would push our plate up and it would rise. And I can give you a practical demonstration of that actually. And this is you may even have seen this before, but here's my flat plate, as you can see. The only problem is this one isn't weightless, so when I let go of one end, it droops, okay? Now, what I'm going to do is I'm going to blow across the top of this piece of paper. And if what I've proposed here and what Mr. Bernoulli says is correct, then by having air flowing across here, it'll produce a low pressure area. The pressure underneath will then push the paper up into that low pressure area. So the paper should rise. Let's see if that really happens. It takes a bit of skill, this, so hold on. Whoops. Do you see that? Exactly what was predicted happens. Where you have air travelling or any fluid, and air is a fluid, anything travelling, the faster it travels, the lower the pressure. The lower the pressure at right angles to the flow. So there you go, and that's basically how wings work. It's one of the theories, it's one of the reasons that wings work, because we have aerodynamic airfoils that cause air to flow more quickly over the top than the bottom, so we get lift, because the faster the flow, the lower the pressure. So if you've got a flow that's really fast over the top and a low flow over the bottom, then the pressure will still be higher underneath than on the top. Okay? Bernoulli's theorem. Got that out of the way. So now it's time to look at our propeller in a tube, in a duct, like this. Now, this is what it looks like, motor, propeller, the tube. We've got a cross-section, obviously, here of what's going on. And what I'm going to show you now is, first of all, we'll talk about how propellers work, because that's pretty important. If you don't know how a propeller works, this isn't going to make any sense to you. But I'll draw a diagram over here. If we look at the cross-section of a propeller, let's do the hub like this, you'll know that it's got two blades, aerofoil, there's one on the other side as well. Now, these blades are at an inclined angle, because we'll draw another diagram of the propeller looking down on it, because we'll get the plan and the elevation here. So there's our propeller looking down on the top. And the propeller, of course, will rotate. And it can rotate in either direction depending on the way we want the thrust to come out and the way the propeller blades are organised. So there we go. Propeller rotates, and in doing so, these blades move through the air like a wing moves through the air. And they work on exactly the same principle. So if we look at how a wing works, I'm going to do a quick revision for those who don't know here. Let's have a wing, and it has an aerofoil section like this. Here we go, and let's have some air. I should use blue for the air. When an airfoil is moving through the air, some of the air comes along and it gets deflected down here, and some of it goes up over the top and is again directed down. So we have two flows, it splits the flow. And how do wings work? I mean, I've already done a video on this on my XJet channel, but I'm going to tell you again quickly. There are two reasons that wing creates lift. First reason is Newton's law. Newton's law says, it's the third law, I can't remember, it might be the first, I can never remember the order, but anyway, Newton's law says that for every action there is an opposite and equal reaction. You know, so when you push someone, you actually feel yourself being pushed back at the same time. What happens here is we've got air coming along, it gets deflected down. So what happens, the reaction is the wing is deflected upwards. Simple. And this is how flat plate aerofoils work. You know, you make a paper plane, it hasn't got a curved aerofoil, it's got a piece of paper. Or you make a thin balsa wood glider, it's got flat balsa, or those styrofoam gliders you press out of a flat sheet. They don't have aerofoils, they actually have a flat plate. Those wings work solely by causing the air to be deflected down, thus producing a reactive force, pushing or giving lift to the wing. But there's another factor that comes in here. This is a bit debated actually. Some people have said, oh no, that doesn't work. But I think if you've just watched my demonstration with the Bernoulli effect, you'll agree this has to play some effect on the whole thing. And that is that the air travelling over the top here, if we were to measure the length of these lines from, say, here to here, you can see that this line is a lot shorter than that line. So what happens is, in order for the air to get right over the top and down here because of the curve, it has to travel more quickly. And in travelling more quickly, Mr. Bernoulli says that if this air is travelling faster than that air, what is the pressure going to look like on this propeller? Well, I will use my red pen to draw what we call a bubble of low pressure. Now this area here, which I'm cross-hatching, is a bubble of low pressure caused by the Bernoulli effect. The air travelling quickly over the top has reduced the pressure up there, so what you then have is the higher pressure below, lower pressure above. Again, you're getting lift. You're getting lift. So there's two factors creating the lift, and it's the same on our propeller. Our propeller is just one of these aerofoils attached to a hub so we can spin it round. So we're going to have low pressure on the top of the propeller and high pressure on the bottom. And little basic, one of the fundamentals of fluid dynamics is that where you have high pressure and low pressure, if there's nothing to obstruct it, there will be a flow from the high to the low. It's simple. You know, it's just the way things go. You know, if you've got high pressure in one area, low pressure in another, you get wind or whatever, but you get flow from the high to the low. And that's what tries to happen on the propeller. Obviously, the low pressure on the top and the high pressure on the bottom means that this high pressure area is always trying to get up the top to fill in the low pressure, because nature abhors differentials. It tries to cancel everything out. Likes to have everything level and even. So it likes to neutralise the pressures. But what can happen, of course, is it can't just go through there because you've got a propeller in the way, a propeller blade. It blocks the flow of air from top to bottom. However, what also happens is that you've got to remember our propeller is spinning round and round and round. Another piece of physics now. Where's my little demonstration I prepared earlier? Here it is. And it may look like an AXN motor to you on some wires, but trust me, it's not. It's a piece of physics equipment. Again, like that piece of paper, this AXN motor just hangs down, right? Doesn't go anywhere. I can make it do this, though, by spinning it. If I spin that, you see that now suddenly the wire is horizontal. The wire is pretty much horizontal. Why is that? What is the force that's making this motor go from hanging straight down to going up like that? Well, it's centrifugal force. It's another one of those things that you find in physics. And basically what it means is that when you spin something around, there is a force exerted that tries to move things to the outside of the circle in which you're spinning it. And of course we've got a propeller spinning here, and it's spinning in a circle. So what happens with a propeller is that we've also got this high pressure, low pressure setup. So we have air actually travelling along the propeller. Because this is spinning around, the air naturally tends to get flung to the outside. So some of the air travels along, and when we've got our high pressure bubble on the top, the high pressure bubble actually gets flung to the edge. So now you can see the problem. We've got high pressure with nothing to separate it from the low pressure on the top, nothing separating it from the high pressure underneath. So we get a flow. We get a flow here from the bottom of the propeller to the top of the propeller. So that basically what happens is, let me draw another diagram here, if I can find my black Sharpie, running out of pens. Oh, what have I done? Lost it. I'm always losing. There it is. Let's draw another one here. Here's our propeller, and here's one blade, the other blade. So we have our low pressure bubble on the top here, and we have high pressure underneath. So the high pressure is being flung out towards the edge, and the low pressure is also coming out towards the edge. So where they join, you get this big vortex. The air curls around because the bottom air is trying to reach the top of the propeller, and in doing so it goes into a circle and creates a vortex. And that, basically, a vortex just means lost energy, wasted energy. The energy that goes into creating this vortex at the tip there where the high and low pressures meet is simply turned into noise and heat. It heats the air, only a very, very small amount, but the air gets heated up, and it makes a hell of a lot of noise because of all the molecular movement of the air, and that's pressure waves making sound. So that's what happens. Now, obviously, if you've got a propeller operating like that, let's draw it on this propeller up here. We've got our low pressure area here and high pressure underneath. How can we stop this vortex, this tip vortex? And the answer is really simple. As you can see, if we just basically put a fence up here, it stops the high pressure from being able to reach the low pressure. It blocks it. It's its physical barrier to the movement of high pressure air to the low pressure area. So suddenly, well, you can't get this vortex anymore. So the energy that previously went into creating that vortex is actually going to be turned into lift, because we're not cancelling out this low pressure area on the top with this vortex flow. So that becomes stronger because it's not being nullified by the flow over the tip. So you're getting more lift from the propeller. And you haven't had to put any more power in. In fact, you need less power because less power is being wasted in this vortex. So when we put our propeller and our motor in a tube, the tip vortex is greatly diminished. It won't go away because there's always a little bit of gap between the propeller end and the thing. So it's always a little bit of leakage, but it dramatically reduces the effect of that tip vortex from the propeller. So we get much more efficiency. And that's why a propeller in a duct, in theory, is going to be more efficient than a propeller just operating in free space. But now, if you thought that was good, if you thought it was cool that we got something for nothing by putting our propeller in a duct, you're going to be even more impressed with what comes next. Because there are two ways that a propeller duct can improve the performance, the efficiency of a propeller. And the next way is actually really, really cunning. And you've probably seen it and didn't realise it. Now, at the moment, we've just got a parallel-sided tube. Just a tube, a piece of pipe, and we'd get that improvement. But if we do this, something really interesting is going to happen. And I'm drawing a nice big curved lip to quite a large radius curved lip on the edge of our duct. So basically we've taken that tube and we've just rolled the edge around all the way around, so it's rolled outwards. And that's going to dramatically improve the amount of lift this setup creates. How's it going to do that? Well, I'm going to draw another line in here so you can actually see something here. Let's draw a line in there and a line in there. And I want you to see if you can spot something else on the board that looks pretty similar to that shape. Oh look, a wing. So yeah, what we have here is a wing. Honestly, it's an annular wing around the top of our duct. And it's going to produce lift. How? Well, let's draw some lines. Let's draw some airflows. Now, obviously, our duct is going to be drawing air in the front and blowing it out the back, whether it has a lip or not, right? So that's pretty fundamental. But what it's also going to do, and when we've got, especially we've got this lip on here, is it's going to draw air around the side here and into the duct. And around the side and into the duct. Now what do you notice about what's going on here? Well, we have a flow of air over a surface. And as we did right at the beginning of this video, when you have a flow of air, the pressure drops. The pressure falls. The faster the flow, the lower the pressure. Now, this, obviously, if we were to draw that lift bubble to show where that low pressure area is going to be, it's going to be all the way around here. Right, and all the way around here on this. And I'll draw the cross hatch so we can see. This is an area of low pressure caused by the flow of air over that lip. And interestingly enough, that's a Coanda lip. I'll talk about Coanda effect in a moment, but suffice to say, suddenly we've got low pressure up here. And remember that we also have no flow over the back of this lip. I mean, there's no airflow here, so we're going to have a static pressure, just the normal air pressure pushing on here. Normal air pressure on there. So high pressure behind the lip, low pressure in front of the lip. What do you get? Well, you get a force, you get thrust, you get the lip trying to move up. You're getting a thrust created by this annular wing at the neck of the duct, creating forward force. So if this is hovering, you're getting more lift because this bubble here is helping lift up the whole duct. If this was tipped over and it was on a plane, so like a ducted fan in a nacelle or something, then this is going to be producing, if you tip this all over, it's going to be producing forward thrust. It's contributing to the thrust generated by the motor itself. And hey, the interesting thing is, it doesn't cost you anything. There's no extra drag created. In fact, there's less drag in the setup than just having a tube. So you're actually getting more free energy, well not free energy, but you're getting more efficiency for nothing. Just having this lip on there. It's called a Coanda, it makes it into what's called a Coanda duct. It's a Coanda lip. And I'll tell you a little bit about the Coanda effect in another video if you like, although I think I've done one on my XJet channel. I think I did a video on Coanda effect on my XJet channel. Can't remember. I'll have to have a look. Suffice to say that the combination of this lip, which is an annular wing, and the ducting itself can produce, in theory, quite significant improvements in performance. And that's what I'm going to do in the next video. I'm going to take that duct that was sent to me, one of the ducts that was sent to me, and the Hobby King thrust stand, and I'm going to hook this up. We're going to test propellers without the duct, and we're going to test them with the duct and see what effective improvement this makes. As I say, in theory it should make quite an improvement, but there are a number of factors which can greatly influence the amount of performance increase you get, and I'm going to go through those and explain what those are, and perhaps in another video as well. One of the key things is the clearance between the propeller and the edge of this duct. Obviously, if you have too much gap in here, then too much of the high pressure air can get around into the low pressure, and you end up with that turbulence and the loss of power. This has to be a very, very close fit, because as you know, through the smallest gap you can blow air. You know, put your fingers like that, still blow through them. You really have to have the gap very small, and we're talking microscopic in some cases. In large gas turbine engines, that gap is incredibly small as a percentage of the total diameter. You know, we're talking just a couple of millimetres on something that may be like 600 millimetres in diameter, and it may be, you know, even just half a millimetre in some cases. And if that gap gets too wide, all your efficiency goes to hell in a handbasket. If you fly gas turbine jet engines, then you will know, possibly through experience, that if the gap between the turbine wheel and the housing which holds the nozzle guide vanes, if that gap is even just half a millimetre too big, then your engine runs like crap. It has little power, it overheats, and it doesn't throttle very well, because too much of the high pressure air is getting to the low pressure side, and energy is just being lost. And you need the energy that goes through the turbine wheel to drive your compressor to compress the air before it goes into the combustion chamber. So it really has a big effect. Anyway, that's how your ducting works. That's how you get all the wonderful things. We've got the Bernoulli effect, we've got centrifugal force, we've got the Coanda effect on the lip there. All these things combine to give us wonderful efficiency. So you might ask, well, why aren't all propellers put in shrouds and ducts? Well, obviously, there's practical reasons against it. You've got the weight of this assembly, the weight of the duct, the weight of the shroud. That produces a downside. You've got to carry the extra weight. And if you're only getting, say you had a setup here and this weighed, 100 grams, and you were getting 95 grams improved thrust, then it's a waste of time because you're still down 5 grams. So that's why we have to do practical tests to see just how much practical difference it makes. And there's one other thing. One other very important thing, especially for multi-rotors. And if people want to know about it, I'll talk about it in a future video. It's about what happens when you start tilting these and moving forward, and why that effectively caused the failure of a very promising project in the US military about, 50 years ago. There was a product, a thing that was built around these ducts, and it looked really promising until they actually flew it and found, oh my goodness, we didn't count on that effect. And I'll tell you what that effect is and why it happens. If you're interested, just ask in the comments so that I know. Otherwise, I'd just be wasting your time. That's another whiteboard video from RC Model Reviews. Thank you for watching. If you've got comments, if you've got questions, critiques, anything like that, just stick them in the section below the description that YouTube kindly provides for this purpose. And now I've got a heap of stuff to do. Got to get back to the editing suite because, oh man, so much footage is piled up there to be edited. And so, but this is really quick. Whiteboard videos are really quick to edit. It's just talk to camera, put it on YouTube. Excellent. Thank you for watching. Time to go. Catch you later.